Okay, so let's move to the next talk, which is going to be from Amrita Mazumdar, who is basically running the show at Vignette AI, which is a spin-off startup from UW focused on video processing. She got her PhD from UW as well. And she's, a computer systems and architecture researcher with emphasis on visual computing applications, which is, dear to my heart. And she's going to talk to us about better video processing through learning. And I'm very much looking forward to the talk. With that, Amrita.
Great, thank you for the introduction. Let me get set up here. So if I hit play, can you see my screen or the presenter mode?
That is in the presenter mode.
Okay, let's see. Still, let's try this.
I think you could put Zoom and Keynote in the same window. Would that help?
Yeah. Let me stop the share and okay, how's this?
Yep.
Great. Okay. So yeah, thank you for having me. Today I'll tell you about some recent work we've done at the University of Washington on using machine learning to improve video processing systems. So in this talk, I'll talk about video processing systems. Video, as we know, is a pretty popular and critical data workhorse in today's computing ecosystem. Some numbers to that effect, like last year, Twitch streamed 75 million hours of video each month. And Cisco predicted a few years ago that video communications would use 80% of internet traffic. I would expect that has gone up. Much of the video that we work with every day and produce is distributed and analyzed in large cloud systems that use deep learning either to better understand the content or leverage this video content as training data for other computer vision pipelines. But using these types of frameworks presents challenges, or using video for these frameworks presents challenges. I'll talk a little bit about some of these challenges, but maybe first I'll start with a high-level overview. Typically, services read video from some sort of storage media and decompress them. They push them through some sets of machine learning, either deep neural networks or other types of things, and generate features from that types of content. So things like the objects in the scene and bounding boxes around them. They might generate some information about saliency or visual importance, which I'll describe later, or some information about foreground and background, textures, scene descriptions. These are all kinds of things that people like to generate from video content using deep learning. And then these features are then used for making some kinds of decisions or observations about your content or processing of it. And what people have been noticing, and this is kind of what Anna mentioned earlier with pre-processing, is that just the act of working with this visual content, like reading it from storage and decompressing it, is a significant bottleneck on systems, particularly because we have had a lot of success accelerating other parts of deep learning pipelines. A recent paper that's going to come out soon shows that decoding visual media takes 20 times longer than doing any kind of detection or processing on it. And this really kind of motivates our work, the idea that video is still stored as frames of pixels and compressed as a group of those compressed frames. And this way of storing your visual content is kind of mismatched with the way we work with it in deep learning systems. Particularly, you want to extract information from it, but you maybe don't care to decompress all the pixels in the video to get at these observations. So This motivates the work that I'll talk about today, which is how can we leverage the information that we can generate from visual content, like all of these learned features, and use them to improve the performance of our visual content systems. So I'll talk about two specific workloads that we've looked to optimize. The first is more of a video streaming and distribution pipeline, and how we can use learned features to improve performance there while maintaining quality. And then after that, I'll talk about some recent work that's going to come out soon on how we can use other kinds of features to reduce decode overheads for video query processing, so analytics and object detection queries. First, I'll talk about video streaming and distribution. So typically in video streaming systems, most applications use video compression to trade off between quality and size. They don't stream individual frames, they compress the content into a different representation. And this compressed representation often trades off on redundancies in video, like fine details, noise, and frequencies that we don't observe very well. You might trade off on color perception. So the idea that when people are watching a video, they might perceive fine differences in some colors more than others. And also fast motion. So if an object is moving quickly through the frame, you might not notice it at such high quality as you might for more stable content. So video compression codecs leverage many types of features that it computes to reduce the size of compressed video content. But recently, more types of perceptual cues have come out, particularly those that are generated by deep learning algorithms. So here's an example. I'm showing a saliency or a visual content importance map. So this was generated by a neural network that figures out, that was trained on eye trackers, and it infers what the places in the video your eye is attracted to looking at. Or what you find salient in the frame. So here on the left, I have a 4K 360 video. It's quite large. My computer fan is going into overdrive already, just playing it. And then on the right-hand side, I have the saliency map generated from a fairly accurate neural network that encodes what the interesting pixels in the frame are. The white pixels are more important and the black pixels are less important. And for this video, only 15% of these pixels are actually salient. So what this means is that most of the content doesn't really contribute to our understanding of the content of the video. Saliency is a well-studied topic, but the observations that a saliency map provides have not really been folded into traditional compression methods so far. It turns out that leveraging saliency information, particularly at like cloud scale, the way we distribute content today, is quite challenging. Just to give you a brief overview, many applications or many implementations use custom or outdated codecs that either perform worse than modern codecs or have complicated implementations that prevent widespread adoption. Now we are quite used to interacting with video storage and data management through APIs that expose details about quality, about the video structure to your data management system. But when people are working with qualities like saliency, some of these abstractions start to break down. And so there's no way to kind of interact between different spatial regions that might be more salient and regions that are not as salient. Yeah, and then finally, it was important that applications can leverage the saliency-based content and make different types of performance optimizations, either on the application level or being able to utilize custom video hardware accelerators, which are quite popular and widespread. And previous solutions for integrating saliency kind of broke those compatibilities. So these kind of drove the design goals of our system. We wanted to work with, not against modern codecs. Over the course of the project, we've switched codecs a number of times pretty seamlessly. We also provide an open API for different cloud storage systems, and we wanted it to be application portable. So you can play back videos that are compressed using saliency on different types of applications or devices that either understand this perceptual compression or not. And you can also continue to leverage hardware decoders for the best performance. This is a very high-level overview of the system that we came up with for Vignette. A video gets uploaded to the system and ingested, after which Vignette uses a neural network to generate a saliency map of this video. You can plug and play different types of models or use other types of perceptual cues if you'd like, anything from like foreground background segmentation or other types of techniques that you might want to compress your video with knowledge of. After generating the perceptual map, you trigger, this triggers Vignette to use a perceptual-based compression implementation. Our implementation is codec agnostic, so you can switch out different types of codecs as things evolve. And as I mentioned, we've done so a few times. Right now, we support H.264 and HEVC, and we're working to build adoption for AV1, which is going to be a popular open source video codec. After you generate your saliency compressed video, we write it to the storage manager with requisite information for indexing and playback for users. And then also, if the application desires, we support using streaming back feedback from eye tracker logs, such as those produced by a desktop eye tracker or a headset from NVR to augment the perceptual information for the video. So Vignette manages the saliency information alongside the video content, and these kinds of feedback loops can allow you to refine the map over time relative to the initial prediction. And this is possible because we manage both sets of information in one system. For time, I'll only go into details about how we do the codec agnostic compression, but I'd be happy to explain more about other parts of the system offline. So Vignette compression uses a feature called tiles to convert saliency map to video encoding parameters. I'll describe to you how this works. So here I have on the left-hand side some video frames, and on the right-hand side, the saliency maps generated from them. And you can, and this is using a neural network that has good accuracy as of recently. And you can kind of see in these pictures how saliency is not necessarily the same as color or edges or some other type of cue that you might extract from your system. After we generate the saliency map, we then use a popular video encoding feature called tiles to divide the saliency map up into regions. So tiles are a standard interface into video codecs that allow you to partition a video into rectangular regions with different parameters. So you can tune, so the video still exists as a single encoded video, but with individually encoded tiles that can have different either quality or bitrate constraints or other types of adjustments. And you can kind of see that the way you divide the video up into tiles can influence how you group the different salient regions together. Tiles are independently encoded, which introduces overhead when you have many tiles in your scene, but this also allows for more spatially aware processing. So a more salient tile you could encapsulate a lot of information in, and then the less salient ones you can, just give less bandwidth to. And that's exactly what we do. We map for different tile configurations. We figure out the best quality to overhead trade-off between different tilings with a given saliency map, and then we encode the video in tiles with that saliency information in mind. And we have some heuristics that we introduce to make this process go faster, but you could also do it exhaustively to figure out the best approach. The results are that you can go from the video on the left that runs at 20 megabits per second to a video on the right that's a 20th of the size. I also have listed the playback numbers. So this is how many hours of playback you can get on a hardware decoder playing the videos. And you can see that like a Vignette video tends to be smaller, and thus you get better playback efficiency on a mobile device. The videos that I'm showing here, we conducted a user study that has a similar kind of setup to what you're looking at. We showed users pairs of videos at different encoded bit rates, and we asked them which one they preferred or thought was better in quality. We found that for videos that were up to 75% smaller, users perceived no difference. And so this is kind of like our bound on how much you can scale quality for a traditional user and still get benefits to using a saliency-based compression method like this. We also quantitatively evaluated the quality of doing this type of compression. We looked at a number of different video benchmark suites. YouTube is statistically chosen to be a representative range of videos on the YouTube of the YouTube library. Netflix, on the other hand, is entirely like very high resolution entertainment content. The VR360 benchmark is 360 projected videos into a rectangular view And these are all like 4K and up. And then the Blender videos, by contrast to the others, are entirely synthetic or like rendered content. So this is a good kind of swath of different types of videos that Vignette might have different performance on. And we measure quality in PSNR, or signal noise ratio. And so on the y-axis, I have SNR in dB, and I'll show columns for each of the video benchmarks. For PSNR, you can imagine that anything above 35 is good, anything above 50 is lossless, and we measure two types of PSNR. So the traditional PSNR does a per pixel quality measurement between a baseline video and the vignette encoded one. And then we also measured eye-weighted PSNR. And so what this does is it looks at the salient regions and it sees, it measures how well we were able to replicate the quality in the salient regions weighted higher than the non-salient regions, which kind of measures how well Vignette does at matching the quality that was driven by the saliency map. Here are the numbers. You can see that across a whole video, we tend to perform better than good. And when you consider the input saliency map as a guide for our quality, we do close to lossless. You can see that for the higher resolution content, our faithfulness is less faithful, because there are more pixels to match against. But across of them, we find that this quality is quite tolerable and provides good performance. There is a lot more discussion about the system implementation and some of the trade-offs for cost deploying this at scale in the cloud that you can find in the paper. But just to sum up, I told you a little bit about Vignette, which presents a compression system and storage manager to manage perceptually encoded video. Specifically here, I told you about saliency compressed video. And using saliency as a perceptual metric, you can reduce storage by up to 75% with little perceived quality loss, which was pretty exciting for us. So that's just one example of how you can use learned features to reduce the size of video content while maintaining good quality. Now I'll tell you about how you can use other kinds of learned features to reduce decode overhead during video analytics. So a similar but different kind of pipeline. So for analytics queries, this is the kind of execution where you are interested in extracting information that has maybe some kind of like meaning from the video content. So as an example query, you might want to select birds from a video. And typically you would do this using some kind of object detection or recognition network. And often people are interested in running these queries and then extracting out the content, or either by drawing bounding boxes and then streaming those pixels out, or just writing all the locations of such objects out from doing that kind of analysis. The same kind of tiled video interface that I told you about for Vignette can speed up processing for a query like this. Tiles, specifically, what's interesting about them is they give you spatial access points into the video. So each of the tiles that I've drawn here is a different way that you can index into the video, and you can just extract out a single tile. So if you had a tile that encapsulated all the objects you were interested in extracting, you don't have to read the rest of the data for the video to get out the pixels that you would like to access. So specifically for these kinds of like subset selection queries, tiles can be pretty powerful in improving the processing of a query analytics engine. But different types of tile layouts can perform differently than others. On the top, I have a equirectangular uniform set of tiles for the video. And then on the bottom, I have what's probably a better way of tiling the video, which is non-uniform. And you can see how different kinds of tile boundaries can, break in between objects, especially objects that move around. The layout on the top might give you better like granularity for things like encoding something like quality. If you were more interested in extracting out information, you would have to decode more tiles to get out the parrots in the top tile layout than the second one. Also, in this example, we're talking about extracting birds from a video, but you might not know what your query is in advance, and you might not understand what the best tile layout is for a given set of queries if they're not known. Also, as objects move around, these tile layouts might also change. What we found is that tiling is helpful in that even if you introduce uniform, so even if you introduce uniform tiles, you can get a speed up, but it wasn't clear how much that performance improvement would be. So here I'm showing a graph. On the x-axis, I have different types of uniform tile layout. So one's like the top tile layout, and these are different numbers of rows and columns. And then on the y-axis, I'm showing the percent improvement on a query over not using having no tiles in your video. So just decoding the whole video. And you can see that even introducing uniform tiles can improve performance. But as you increase the number of tiles a lot, the overhead from having many tiles and decoding them can outweigh the benefits of subset selection. And particularly, you can see that as the number of tiles increases, the variation of within the performance improvement increases more. So this indicates that even though tiling can be helpful, an optimal performing tile layout is probably best and is also query and video dependent. So to address this, we developed TASM, which is a storage system for video analytics queries. TASM incrementally tiles videos based on observed queries over time. So here you can, I'm showing TASM interacting with some query processor where you might have a query like selecting dogs from a video. And once it's observed that we are querying for a specific object, it logs the the object's locations as the possible good layout for the tiling. Over the course of multiple queries, it logs different types of tile layouts that you could incorporate. So as you get multiple queries, you can imagine tiling either for the specific objects or for a combination of them. And then over time, TASM figures out when the estimated cost of doing the tiling is less than the the overhead of decoding the whole video, and then it tiles incrementally to support the queries as they come in. You can also imagine in a situation where you might not have a query, TASM can initially tile based on some guess of what the interesting areas of a video might be. So using something like region of interest or some other kind of segmentation like saliency. This kind of bootstrapped initial tiling configuration helps process the first object detection queries and gives you the performance boost that you get from tiling. All in all, TASM contributes an incremental approach that helps reduce decode pressure during the query processing pipeline. If you, we evaluated on the visual road benchmark, which is a benchmark of synthetic traffic cameras around a city, and ran queries for selecting for cars or people. And Visual Road has a few different video data sets with different resolutions ranging from 2 to 4K. And we compare TASM's incremental retiling approach to having a non-tiled video on these queries. And you can see that overall, TASM provides speed up over using conventional videos and reduces runtime by 12 to 39%. Our speed up is more pronounced for the higher resolution videos because we reduce the amount of content needed to be decoded for these larger volumes more. So to conclude, I told you about a way that you can leverage object detection and object information to improve video analytics performance by enabling spatial random access for queries. We get a speed up on queries for different types of objects as they're observed, 50% on average up to 94%. So that over the course of this talk, I told you about how observed features from machine learning workloads, either perceptual or semantic data, can improve aspects of existing video analytics systems. And if we go back to this kind of high-level overview of what these kinds of pipelines look like, the work that we've been doing is looking at how we can leverage features that you compute using deep learning to improve the storage and management of video data for these pipelines. Ultimately, these insights at best are written to storage to be used alongside the content, but you still end up having some bottleneck from having to work with the video data at all. My guess is that as our systems and machine learning become more sophisticated and as they run faster, we might be able to break that back edge and reduce a lot of the storage and data movement bottlenecks that come from having to manipulate high resolution image and video content by working with features and generated parameters from neural networks and machine learning algorithms that were computed earlier on in the pipeline. So you can imagine that I might be able to have a video that has cats or dogs or whatever and extract out all the interesting information and then be able to keep that video in colder storage and just store that information that is actually important for the rest of the compute pipeline. And longer term, I see this vision as shaping out into a kind of way where visual media storage is much more disaggregated from the processing you do every day. The progress in generative and hallucinative neural networks kind of leads me to believe that you could imagine downsampling your gigabytes of video training data into the learned features necessary for different types of pipelines you imagine doing, and storing just those features in more efficient caches. And then when you do want to access that visual data, you could do a costly fetch of the original video from archival storage, or just render it from generative networks that produce a tolerable result for your needs. So personally, I see these kinds of tile-based approaches as like a step along the way to that future. We are carving up our video into the useful pieces of information that we're interested in accessing from it, some of which may need to be represented by pixel data for legal or accuracy reasons, but other parts like textures, background can probably be faithfully discarded and regenerated when appropriate. So that's kind of how I see things going. I'm pretty interested in what these systems might look like and how you might design for them. So I'd be happy to talk about that too. But thank you for listening. I'm happy to take questions now. Yeah.
Oh, thanks. Thanks a lot, Amrita. I guess we have lots of questions. We can start from the chat. Well, it happens to be that the first question was from mine. I was just curious, saliency, if you want to leverage saliency in VR or in any, I guess, saliency suitable scenarios, is eye tracking a bottleneck? I mean, it's not, I mean, my impression is that it's notoriously slow and power hungry. And so are you relying on that?
Oh, for VR specifically, we are relying on eye tracking as being a source of information to improve your compression offline. So this is different than kind of like the critical path that you see for something like foveated rendering, where eye tracking drives the whole render process. Instead, I think like saliency can be imagined as like your initial guess, and then like in your offline like update to your video storage engine, you might see like what are the popular videos, do the eye tracking logs differ greatly from the saliency maps that we've generated, and can we use it to improve the streaming performance for those specific ones? Yeah.
Okay. I'll skip my questions. If we have time, we can come back to them. Next is from Eric.
Oh, did you want me to ask directly? So just reading what I wrote, apropos of the previous talk, is this salience approach that you've been describing suitable for autonomous vehicles, and could it be used to focus enhanced examination of certain areas around a vehicle?
Yeah, that's a good question. The autonomous vehicle workloads, in my opinion, have, you know, like safety, as the previous speaker said, is a critical issue. And I think that you probably want to be judicious with the type of network that you use to make these kinds of priority decisions. I wouldn't necessarily use salience, which is pretty general and coarse, like it describes importance, but totally reflecting human visual attention. It maybe you could come up with some sort of model that has like perceived objects of importance for the driving workload. And I'm sure that there are networks that people are using in autonomous vehicles that say like, oh, here are traffic signs, here are lights, here are people. And that kind of model could be used to kind of, you know, prioritize the camera streams like content. But I think those networks are much more online than compressed video. So maybe the way that you encode it is differently for those workloads.
Thank you.
Yeah, good question.
Next one is from Kauta. Are you still there? I guess you are.
Yes. So my question is just on the applicability of the Vignette, a platform described. Is it deployed in any production systems? And what do you see are the biggest applications that could leverage the Vignette system?
Great question. Thank you for asking, because currently my day job is in commercializing Vignette as like a production service. And so initially we were thinking that the most applicable production environment would be in video streaming, like particularly for entertainment content that you hear about things like Netflix encoding at many different types of like bit rates and resolution pairs for different types of viewers. And the initial guess was that a service like Vignette would be helpful in generating encoded versions of the content that would work well in constrained bandwidth environments. But we did a bunch of customer discovery and found that the most applicable kind of customer is actually in edge data centers, where they have many more constraints on the types of or they have many more constraints on like the storage and capacity available, but they are also distributing a lot of video content and caching a lot of it. So that's the place where right now I'm working with some potential like interested parties and using Vignette for those types of services.
Thank you.
Okay, thanks, Amrita. I guess in the interest of time, we can take the rest offline. So thank you very much for the exciting talk.
Yeah, thank you.
I guess this concludes this session. So we're going to have a break of 20 minutes. And so we'll see you at 3:15 Eastern time.